The molecular shape has a great deal to do with the polarity of a molecule, and polarity is really important in many chemical and physical properties of different compounds. We've talked about polar and nonpolar bonds, and now we're going to expand on that. If we have a diatomic molecule, meaning two atoms, diatomic molecule, if the bond is polar, then the whole molecule is polar. So hydrogen and chlorine. The hydrogen is less electronegative, the chlorine is more electronegative. There's a net dipole moment of a negative, partial negative charge on the chlorine. So this is the notation that we were familiar with earlier, the delta plus and the delta minus. So the chlorine end has a higher electron density, it's got a partial negative charge. The hydrogen end has a lower electron density, it's a partial positive charge. And this is, we talked about the little boys and whose house was cooler and where were they going to spend more time. It's going to be lopsided here. Another way to represent that is with an arrow. And I think of, mom's coming out. Did you see Johnny and Tommy? And the neighbor points. They went that way. The arrow points to the more electronegative element. It points to the cool house. And then, just to add emphasis, we put a little plus on the other end of it. This is the plus end, and it's pointing to the negative end of the bond or the molecule. So those are two different notations that we use to indicate polarity of a bond or a molecule. So diatomic molecules, pretty straightforward. If the bond's polar, the molecule's polar. If the bond is nonpolar, the molecule's nonpolar. In a polyatomic molecule, it gets a little more complicated, and it depends on the geometry. If the dipole moments of the individual bonds cancel each other, then the molecule will be nonpolar. So you can have a molecule that has polar bonds, but the molecule as a whole is nonpolar. So let's look at that. Let's look at carbon dioxide. And we've looked at this in terms of shapes of molecules. Carbon is double bonded to this oxygen and double bonded to that oxygen. There are two electron groups, and they are on opposite sides. It has a linear geometry. If we look at the individual bonds, a carbon-oxygen bond is a polar bond. The oxygen is more electronegative, so the arrow is pointing to the oxygen. So this dipole moment is going that way. And here carbon with a different oxygen, that's also pulling electron density away from the carbon. Well, dipole moments are vector quantities. Do you guys remember vectors at all? Yeah, some of you do. Do you even just remember hearing about that some point in your math life? Vaguely? Yeah, okay. So a vector has direction and magnitude. And the direction for these dipole moments is going to point toward the more electronegative atom. The magnitude of that will depend on the electronegativity difference between the bonding atoms. If the difference between oxygen and carbon is large in electronegativity, then the magnitude of this dipole moment will be great. If the difference is small, the magnitude of that will be small. Let's go back to this one. So one way to think about this is to think about playing Tug of War. And here you've got a guy standing in the middle, and he's kind of wimpy. He's less electronegative. And here you have a strong guy and a strong guy. They're more electronegative. And they're pulling. And this guy's pulling to the right, and this guy's pulling to the left, but their forces are opposing each other. So provided they don't pull this guy's arms off, right, is this guy going to move if he has guys of equal strength pulling on him from opposite directions? No, nothing is going to move. There's not a positive end and a negative end to the molecule. Overall, it's the same. So we say that those dipoles cancel out. They add up to nothing. Let's look at something else that has two vectors. Water. Water has two polar bonds, but water has a bent shape. It's not linear. So here we have oxygen to hydrogen. The dipole moment is going towards the oxygen, and in this bond, oxygen and hydrogen, the dipole moment is going towards the oxygen. There is a net dipole moment. We'll get to more graphically looking at how you add vectors, but for now I'll stick with the tug of war. So here you've got the strong guy, and he's pulling against hydrogen, the weakling, in this direction, and he's pulling against this guy in that direction. There's going to be net movement now, and he's going to move this way and drag both of those guys with him. They're pulling away at angles, but he's stronger, and he's got an angle on them, and so there's going to be movement. And so this end of the molecule will be partially negative, and this end will be partially positive. And we get that by adding these two vectors. They don't add up to zero. So to look at the polarity of a molecule, we need to look at the Lewis structure and find the molecular geometry. That's the Vesper theory. Then we need to see, does the molecule have polar bonds? Oftentimes the molecules do. And then you draw the polar bonds as vectors pointing toward the more electronegative atom. The length of the vector would depend on the difference in electronegativity. That's not going to be a huge deal. Then you determine, do the polar bonds add together? If they add together to zero, then the molecule's nonpolar. But if there's a net vector, the molecule's polar. So let's look at vector addition. In one dimension, it's relatively simple. So here we have a vector of +5 going from left to right and +5 going from left to right. We're going to add these two together, and we're going to get +10 in that same direction. We're adding these together. In this example, we have 5 going to the left, a -5, and a +10. We add those together, and we get +5 to the right. Are you with me? Here we have -5 and +5, and those add up to 0. They are opposite in direction and equal in magnitude. They're going to add to 0. These are opposite in direction but unequal in magnitude. They will not add to 0. These are equal in magnitude, and they're in the same direction, so they'll actually add on top of each other and become larger. So that's one dimension. Any questions about one dimension? And we're going to go to 2 dimensions. 2 dimensions. You're going to draw the vectors. So here's this vector going that way and this one going this way. Then you draw a parallelogram, making the vectors 2 of the sides of the parallelogram. Remember, a parallelogram has parallel sides, but the angles can be different than 90 degrees. So it's related to a rectangle, but it's a rectangle that can kind of squish and tip over a little bit. So here this line and this line are parallel, and these 2 lines are parallel. And to add the vectors then, you go from corner to corner, and this is the result of adding vectors A and B. Here's a different example. Is you just draw them, and then you complete the parallelogram, and adding them together is from the corner you're starting at to the opposite corner. Any questions? When you have 3 or more vectors, things get a little more complicated, and they're often going to be in 3 different dimensions, not just in 2 dimensions. But you take them 2 at a time. So here in example 6, we've got vectors A, B, and C. So first, we're going to add A and B by making that parallelogram, and we'll get this vector R. Then we'll take R, the red one, and add it to C, again making a parallelogram, and we'll get the purple one. And that's the result of adding all three of those vectors together. Here's another example. When we add A and B, we get this red vector here. And when we add that to C, it adds up to 0. So this is three vectors pointing in opposite directions. They're going to cancel each other out, essentially. They add up to 0. So if the vectors of your polar bonds are something like this, there's going to be no net polarity on your molecule. So common cases that we encounter with molecules. Linear molecules are the easiest to understand. If the dipole moments are the same in magnitude and going in opposite directions, which, if both of these atoms, like if this is oxygen and that's oxygen, the difference in electronegativity is the same. And so you have forces that are equal and they're opposing each other, and the net dipole moment is 0. If you have a bent molecule, you're most likely going to have a polar molecule because these are going to add together to form this vector. It's not going to be 0. With trigonal planar and tetrahedral, we will often end up with nonpolar molecules if all the vectors are the same in magnitude. They'll cancel each other out. Trigonal pyramid will usually be polar. Okay, so I just want to show you something. It's kind of a cheat. Maybe it's a molecular polarity hack, right? So just by looking at the Lewis structure, this works most of the time. The molecule is nonpolar if both of these are true. 1, no lone pairs on the central atom. If you see lone pairs, it's probably going to be polar. So if there's no lone pairs, and, I should put the and in here, big and, it's got to be both, and atoms bonded to the central atom have the same electronegativities. That's important because if the electronegativities are different, then the magnitude of the vectors is not the same and they won't add to 0. So examples, if we look at water, we look at the Lewis structure. Are there lone pairs on the central atom? Yes. Done. Polar. What about methane? Any lone pairs on the central atom? No. Are all the atoms, do all the atoms bonded to the central atom have the same electronegativity? Yes. Yes. I left out a word here. So then what can we say about this molecule? It's nonpolar. Usually this little hack will give us the same results as thinking about adding vectors. What about this one? That's going to be polar. There's no lone pairs on the carbon, but oxygen and hydrogen don't have the same electronegativity. There's going to be a net dipole moment, and so this is polar. Any questions? It's not foolproof, but it works most of the time, and it's easy. And so something that's easy and works most of the time is pretty good in my book. Let's determine if CF4 is polar. Well, we have to look at the Lewis structure. So we've got carbon and 4 fluorines. And we've got 4. I'll show you kind of a less tedious method of figuring out how many lone pairs to put in here. So here with the carbon had 4 electrons. There's 1, 2, 3, 4. Half of those bonds are carbons. And then here's 1 from the fluorine, and then fluorine has 6 others, a total of 7. And so that's going to be the same for each of these guys. So what I'm doing in my head is I'm saying, okay, those are fluorine's electrons that he brought in, and these are fluorines, etc. And here's carbon, and it brought in 4. And so I can see that I have the correct number of electrons in my structure. Just remember when you're doing Lewis structures that the electrons do not have to stay with the atom that they came in with. Sometimes they move around a little bit. So there's our Lewis structure. What's the fast and dirty way say? It says nonpolar. No lone pairs on the central atom, and all of those atoms bonded to the central atom are the same. So let's do the more thorough thinking about it method. What's the molecular geometry around carbon? It's tetrahedral. So here's carbon, and it's going to have a tetrahedral shape with those fluorines. Well, the tetrahedral shape has these evenly spaced around. And what that means is if the magnitudes are the same, they're going to sum to 0. To determine the magnitudes, we have to look at the electronegativity difference between carbon and fluorine. Well, it's the same for all of these. If this was chlorine or hydrogen or something, we would have a different outcome, but we'd have a different outcome from the fast and dirty method too. But these are going to be equal magnitude vectors going in opposite directions, and they're going to sum to 0. So that's a nonpolar molecule. Any questions? The polarity of a molecule has a big impact on its physical and chemical properties. So we know from experience that oil and water do not mix, right? Think of Italian salad dressing, and you can shake it up, and as soon as you set it down, the oil starts to rise to the top, and the vinegar, water, and most of the spices are going to be at the bottom. It just does that. Why? Well, it's because oil is nonpolar and water is polar, and they don't mix well. I really like this analogy. So these solid colored marbles are magnetic, and these that are mostly clear are glass marbles. The magnetic marbles are attracted to each other. They're going to stick and clump together. And if there's a glass marble that somehow got in among them, it would get squeezed out, wouldn't it? These guys are so attracted to each other and they form such a tight group that they squeeze these guys out. Now you could take this into social relationships in high school too, couldn't you? This is a really tight clique, and these are the people, they just can't get into it. They can't get into the clique because they're being excluded. What happens with the polar molecules, here's diagram of water, it's got a partial negative end and a partial positive end. The positive end of one molecule is attracted to the negative end of another molecule. Just like these magnetic marbles are attracted by the north and south poles. And so there's this force of attraction between them. That does not happen to nearly, not even close to the strength that it does. Start over. That sentence went badly. Nonpolar molecules don't do that. Polar molecules, because they have this charge, they have this attraction between the opposite charges. Nonpolar molecules don't have that. Did that make sense? Okay. It wasn't very good. Which leads us to how soap works. This is, if you printed out notes, I'm sorry, the pictures were in the wrong place. So we know that grease and oil don't just rinse off with water. If you've been working on your motorcycle, or you've been baking, and you had to grease a pan and you've got Crisco on your hand, you can't just stick your hand under running water and have it come off. It's really different from, say, getting sugar on your hand. You're eating a sugar donut and you get powdered sugar on your hand. You stick your hand under running water, the sugar washes right off. Grease and oil, it doesn't work. You have to use soap. It's just not going to come off otherwise. Because water is polar and grease is nonpolar. And they're not going to mix together. So what does soap do? Soap is really cool stuff. Soap has a polar end, we tend to call it the head, and a nonpolar tail. So it kind of looks like a snake, where here's the head and this is the tail. So at one end it's polar, and at the other end it's nonpolar. And so what happens is this polar end can mix with the water, and the nonpolar end can mix with the grease or the oil. And we need a picture of what this actually does. So what happens is, here you've got your glob of grease. Okay? The grease all wants to stick together because the water is excluding it, and we need to get the grease into smaller pieces and escort it through the water. So what happens is the polar end of the soap will be out, and the nonpolar end will be towards the grease. And it'll be surrounded by these little soap molecules. And this forms what's called a micelle. I won't test you on that, but there it is. It's a micelle. So this little micelle can sneak through the water because it's got these polar groups on the outside. And polar and nonpolar is a little like speaking different languages. And so because this is being ushered by polar-speaking agents, it can pass through the water instead of being excluded and having to stay with its nonpolar-speaking friends. Does that make sense? Soap is good stuff.